Hello members, in this video we are going to look at a chi-square, and this is majorly used in statistics. So this is in statistics. So a chi-square is a statistical tool used to assess the relationship between categorical variables. It helps to determine whether the observed frequencies in a contingency table differ significantly from the expected variables under the assumption of independence or a specific distribution. The chi-square test is versatile and can be used in various scenarios, but its most common applications are as follows. So we find that the chi-square is used in the chi-square goodness of fit test. So the purpose is to determine whether a set of observed frequencies matches an expected frequency distribution. An example can be, suppose you have a die and you want to test whether it's fair, then you roll the die a number of times and then count how often each face appears. Then the chi-square goodness of fit test helps determine if the observed frequencies match the expected frequencies, which, for example, for a fair die would be equal for all faces. So this is one scenario where we can apply a chi-square. Then we have a chi-square test of independence. So you find that sometimes you want to test whether two categorical variables are independent of each other. Suppose you survey a group of people about their preferred type of music. This can be pop, rock, classical, and their age group, e.g. young, middle-aged, senior. Then, the chi-square test of independence can help determine if there is a significant relationship between age group and music preference. So, you can see that a chi-square is very important, of course, in statistical analysis that involves categorical variables. The chi-square test for homogeneity, this is the third one, and this can also be used to test whether different populations have the same distribution of a single categorical variable. Suppose you want to compare the preference for a new product across regions. The chi-square test for homogeneity can assess if the distribution of preferences is the same across these regions. Okay, so you want to test for homogeneity, then you need to go for a chi-square test. Okay, then we said also there is a chi-square distribution. So you can also do this test. The chi-square distribution is a family of distributions that are defined by the degrees of freedom, which typically depends on the number of categories or groups in your data. Okay, groups in your data, and it's positively skewed, meaning it has a long right tail, but as the degrees of freedom increase, the distribution becomes more symmetrical and approaches a normal distribution. So let us look at how a chi-square works. So the observed frequencies are the counts that you actually observe in your data. If it is an experiment, this is what you observe. The expected frequencies, these are the counts you would expect to see if the null hypothesis was true, if the variables were independent, or if the distribution followed a specific pattern. Then what you are talking about here are expected frequencies. You could have a proportion of uh, performances, and then you need to use those proportions of the different categories to see how each performs under its own ratio. So at the end of the day, you are able to get the expected frequencies. Then the chi-square statistic. This is how we get it. So we have this being a statistic that quantifies the difference between the observed and expected frequencies, and the formula is here. You get the observed frequency for category I, then minus the expected frequency for category I divided by, of course, squared, then divided by expected frequency for category I. Then I sum all those values, and what I will get, it will be x squared. So I might have a value, I mean a category, and it's a chi-square statistic could be like this. So that will be O1 minus E1. This is squared divided by E1. Then I have x2 squared is equal to O2 minus E2. This is squared divided by E2 until I finish all of them. Then later on, I get the chi-square value from x1 squared plus x2 squared dash dash up to xn squared. So that's very important to know. How about interpreting the chi-square test? So we'll have the null hypothesis, H naught, typically says that there is no association between the variables, and these variables are independent of observed distribution fits the expected distribution. So we are saying that the variables which could be independent or observed distribution fits the expected distribution. Then what we are saying being the alternative hypothesis, H1, suggests that there is an association between the variables, or that the observed distribution does not fit the expected distribution. So that is what we are calling the alternative hypothesis. So sometimes you also need to get the p-value for this chi-square test, and this is as other hypothesis testing. So the chi-square test results in a p-value which you would compare to a single level, I mean a significance level, commonly around 0. Have alpha equal to 0.05. Okay, if the p-value is less than the significance level, then you reject the null hypothesis. Okay, so in summary, we are saying the chi-square is used to compare observed data with expected data to see if there is a significant difference. Then it's commonly used in the goodness of fit, test of independence, and test for homogeneity scenarios. The chi-square statistic measures how much the observed data or value counts, deviate from the expected counts, and it is compared against a chi-square distribution to determine the significance. So sometimes if you're given a scenario, you find that you can be able to determine whether the difference that we are talking about between the observed and expected outcomes is significant. And you can always compare. You have a critical value from the table. Okay, you have a critical value from the table, and the chi-square statistic. So the one that you have calculated, this is the x squared that has been calculated. So you compare the two and see if there is one which is going to be greater than the other. So if I, for example, put them on a number line, I'm coming from 0, and maybe this happened to be my chi-square critical, okay? Then maybe this is the chi-square calculated. So by the fact that the critical one is less than this, that means I'm going to be almost in the rejection region, and therefore this is going to tell me that I can reject the null hypothesis. Okay, but if the calculated one, is less than, okay, if the calculated one is less than the critical value, then we shall say we can't reject the null hypothesis. We shall say fail to reject the null hypothesis. So if you fail to reject the null hypothesis, that means uh, you will take the alternative hypothesis. So this tool, the chi-square statistic, or the chi-square itself, is crucial in fields like genetics, marketing, social sciences, and any other area where categorical data is analyzed. So now, hello members, in this lecture, we see how we can calculate the degrees of freedom for any type of a chi-square test. So now let's look at the chi-square test goodness of fit. And for the goodness of fit test, the degrees of freedom are calculated as the degrees of freedom equal to k minus 1, whereby k is the number of categories or groups. Assuming you had, for example, 3 categories, okay? So that means your degrees of freedom will be 3 minus 1, and that gives you 2, okay? So what about if we are looking at the chi-square test of independence? For the test of independence, the degrees of freedom are calculated as follows. We have the degrees of freedom equal to rows, the number of rows minus 1 into the number of columns minus 1. So whereby, of course, we are saying R is the number of rows in the contingency table and C is the number of columns in the contingency table. The chi-square test for homogeneity is the same as that for test of independence, and therefore it shall also be degrees of freedom equivalent to the number of rows minus 1 times the number of columns minus 1. You could be looking at a particular category that has, for example, I may say you have females and males, and maybe the colors of shirts or the colors they like for their dresses or for their dress codes. So you can have, for example, blue, you look at white, maybe green, etc, etc. Then you have M, and that is male. Then you have female. Okay. Now each of these has got the observed and then the expected. So you have values in here. Okay. You have values here. So now this is going to be, for example, observed for this. So you have 1, 2, 3, 4. So you can put the total here, and for the female you put the total, for green you put the total, for white you put the total, and for blue you put the total. So when you're looking for example, expected So for the male, you'll find that for you to get the expected value for the male here and for blue, then it will be you will get the value for blue divided by the total for blue, then you multiply by the total for male. Like that, like that, like that. So here, to get the number of degrees of freedom, it would be the number of rows. Okay, number of rows are 1, 2. So this will be 2 minus 1 into how many columns? 1, 2, 3 into 3 minus 1. And the number of degrees of freedom will be 1 times 2, which gives you 2. So given that you have 5 categories, for example, different colors, the degrees of freedom, if we are talking about goodness of fit test, then it will be K minus 1. So whereby K is the number of categories, and if the categories are 5, then the degrees of freedom would be 4. If you have a 3 by 4 contingency table, you have 3 age groups and 4 product preferences, you'll find that the degrees of freedom will be 3 minus 1. Of course, those are the number of rows. Then columns are 4. So you'll find that the degrees of freedom are 6. So here we are saying that for the goodness of fit test, the degrees of freedom are based on the number of categories. For the test of independency and test of homogeneity, the degrees of freedom are based on the number of rows minus 1 times the number of columns minus 1 in the contingency table.